Hi, everyone. I'm Michael.
I'm Ziran.
I'm Praneet.
I'm Andrew.
I'm Brian.
And we are the Intelli group. So, next slide. So, basic agenda of what we're going over today. Just go ahead and go to the next slide. So, our basic goal is to have a braking system that will be able to stop an object, or stop a moving object that has another object on top of it, such as this cylinder, and stop in time to not hit a wall and keep that object that is on top of it from toppling over. In other words, we don't want what is going to happen in this video. All right, so the things that our system would need, there's a few things. So first off, it would need to sense certain things. The first thing would be a distance, because it would need to figure out how close it is to a wall. And it would also need to figure out its velocity/acceleration, so it can determine if it's going too fast, if it needs to slow down, and if too much brake is being applied. For an actuator, we need to apply a brake, so we need to have something that can control the onboard braking system. And we also need to figure out some form of a model that can accurately determine what it should do in each scenario. So the hardware that we're actually using is the mountain board, which comes with its own brake, an Arduino Nano to control the system, a servo to attach to the brake cable, an ultrasonic distance sensor to figure out how close to the wall it is, and an accelerometer to get, for our cases, both acceleration and velocity. The software that we're using for simulations is MATLAB and Simulink. And here's just a basic diagram of all of our different pieces of hardware. Good.
I'm going to talk about the simulation and modeling approach that we used in this project. Quite different from what we thought we would do at the beginning. We created a conceptual model for this object very early on in the project, and we built our algorithm around that project. And then we created this MATLAB Simulink model in MATLAB and trying to predict what the behavior of the system is going to do. And a key question that we need to answer in modeling is we're sensing acceleration using accelerometer, but we wants to know is this superior to use acceleration as a trigger of the braking system, or we should integrate the acceleration and use the velocity at that moment to trigger the braking system. And in the model, in the simulation in MATLAB, it turns out it doesn't depend very much on either one works just fine. But in reality, we find out that velocity, actually using a velocity-based triggering system, that is actually superior in our application. And my teammate will probably address why it is so and the challenging part of this system. And based on modeling and simulation MATLAB, we find out that our system is kind of noise sensitive. When I put noise into our integrated velocity measurement, and the system behaves quite differently from the ideal case where there's no noise and quite different modeling philosophy. So, and simulating philosophy is the simulation is not sort of worked as a guideline of our coding in Arduino. Instead, I was sitting next to these guys and constantly change my model in simulation and use the simulation as sort of a guideline to predict what our changes in code gonna do to our actual behavior of the board. And that results in a numerous amount of model and simulation was produced, and I will present the last close to the one that we have on board right now. Okay, so this is the model that we create in Simulink. So So we have a source over here, basically generate the sort of simulate this the sensors, the distance sensors, and outputting the distance to target, which is the wall at any given time, and that is given to this function that does a calculation to calculate the desired velocity we want the system to be in at this moment, and that is get compared to the actual velocity that we calculate from the acceleration readings on board on the accelerometer. And the difference is taken into account as an aero turn and brake handling sort of system where we physically set the angle of the servo and to apply a certain amount brake proportional to our difference of our ideal velocity at that moment and the calculated velocity at that moment. And this output of the theta, which is an angle of the servo, is feedback to our acceleration measurement as if we're given a certain amount of angle and we're experiencing a certain amount of the deceleration in our system. And I will show you some of those key scopes that was generated from this plot. So this, I forced the distance to target as a downsloping piece of a quadratic equation. So this is the distance to target with respect to time, and that generated a desired velocity over time by giving the parameters of the cylinder on top of that and using some physics equation. And this is our current velocity measurement that was integrated from the acceleration we actually experienced. The difference is this curve over here. As you can see, it started pretty big, and we started apply some brake, and then it slows down, and we approach an overshoot and come back up, and this is the end of the simulation. And this difference, this arrow turn, was fit into our setting the brake turn. So this is the angle of the servo, as is minimum is 1400 and maximum allowed is 2000 in terms of the unit that we used in this case. And as you can see, it start braking and start to after the arrow turn became negative, it starts to releasing the brake and braking again, release the brake and braking again, and this plot shows that, well, this is integrated over the actual velocity we sensed, and we can see that I started the simulation at 5 meters, which is the maximum range that our distance sensor can sense. As you can see that our system stopped just right before the 5 meter mark. And as I added noise to the velocity as integrated, which is this curve, I can go to the next slide. Next slide. So this is to demonstrate that as I adding a small noise to the velocity sense data that we used in this simulation, as you can see, we have quite a different servo response and quite a difference acceleration profile simulated. And I didn't include it here, but the actual distance that we travel is a little further away from the wall due to this arrow was produced by this acceleration. By this added noise into the velocity integration. And I have Andrew talking about some of the major challenges that we worked with this software and the algorithm that we're working with.
So the main goals of our braking system is how do we translate a desired acceleration or desired velocity into actual deceleration or actual velocity. And this is really challenging because the brakes are very uncertain. We don't actually know how much a given value of theta is going to correspond to an actual deceleration quantity or decrease in velocity. So basically, the point of the braking strategy is how do we either determine this theta, how much theta will correspond to how much acceleration or velocity, and once we've, if we can't determine it beforehand, how do we sort of dynamically adjust on the fly to make it so that we can, so that we can actually approximate this value. So if you remember from the milestones, our strategy then was to basically try to pre-compute it, is to say, all right, so basically for a given acceleration in a given distance, if we apply theta x, that will lead to deceleration y. But unfortunately, there are just too many variables there, and it's really due to memory limitations in the Arduino and just the fact that it's just so uncertain. An approach like that would not really have been feasible. So we decided to move on to just, as we go, we give it a velocity, and the servo will just sort of test values and slowly adapt and ideally converge to the desired velocity or the desired acceleration. So our first attempt at that was just binary search. We have servo min, servo max. These are the max. This is the whole range of the servo. And given a desired velocity, just basically test values until we converge on that velocity. And a key component of this, using binary search, a key component of this is we expect the servo to respond very quickly. It has to respond incredibly fast because we want it to converge as fast as possible. And if there's any real delay, we might expect it to take 7 or 8 iterations of this to really just sort of converge on the value that we want, which is not great. The other reason why this is a problem is because while we're doing the binary search, we have to hold the desired velocity constants that we can converge on that value. But it's always changing according to the distance readings. So really, this doesn't really work. It's not responsive enough. So if you move on to the next one. So the next strategy that we tried to do, and this is the one that we actually ended up doing, was a proportional braking system. So we give the braking system a delta, just a difference in velocity, because we're going with a velocity-based approach. So a difference in velocity. And once we have this difference, we sort of divide it by some desired velocity, some quantity that will sort of scale it down. So we get some range. And then that corresponds to a delta theta. So larger differences in the desired velocity and the actual velocity will correspond to larger changes in theta. And similarly to the binary braking system, or binary search braking system, this will eventually converge to what we want, the desired velocity. The problem with this is that there could be so the problem with both of these approaches actually is that we expect the servo to be very responsive. But what that means is that while it's converging, there might be very, very high instantaneous decelerations. And so one of our earlier strategies was to say, well, there might be a very high instantaneous deceleration. That might cause the cylinder to tip slightly, but if we can detect that and correct for it, we can actually, that doesn't really matter very much. Ultimately, we didn't actually go with that approach, but we still found that the solution worked reasonably well. So this is what we chose for our braking model.
So one of the biggest challenges we actually faced was designing the velocity sensor, for our platform. And basically, what we started with, if you remember, was actually reed switches. So basically, we'd mount the reed switch to an axle, and every time the wheel would go around, basically we're trying to build a rough encoder for wheel RPM. So every time the wheel would go around, a magnet was supposed to, flip this reed switch, fire off an interrupt, and increase the RPM counter. But the only problem with this was that not only were the reed switches inconsistent, they were actually very physically fragile. So we actually broke a couple, just trying to bend the leads and mount it onto the breadboard. So, and every time I would bring a magnet close to it, it would bounce. So not only would it register just one click, it'd register multiple clicks at a time. So this was just on the breadboard, so let alone mounting this on the actual vibrating platform. So we decided to kind of scrap this idea and use a limit switch instead. Basically, all a limit switch is just a lever arm that points out. And every time it would be mounted on the axle, so every time a wheel would go around, each of the spokes would just bend this lever arm, do the same exact thing as firing off the interrupt, increasing the RPM counter. However, this was more robust than the reed switch, though the results that we got were still fairly inconsistent. Every time the switch would close, every so often we'd get 2 clicks or 3 clicks, and this would mess up our calculation algorithm that was dependent on these RPM ticks. So ultimately what we decided to do was just kind of scrap the velocity sensor. It was just too hard to get consistent values, and this would throw off all our other acceleration values. So we decided to just use the accelerometer reading, and using the accelerometer values that we'd integrate over time, we'd calculate velocity from that.
So one of the main challenges that we had to face was, are we going to make this a velocity-based approach or an acceleration-based approach? And so ultimately, the idea was that we decided to choose velocity because we found that it just gave us better readings in general. With the acceleration-based approach, we would be using values for the current acceleration to try to determine what we should do next. The problem with that was that this thing is bouncing all over the place as it's going. So and also because we're moving at such low velocities and with such small acceleration values, we required a great deal of precision. So that combined with a ton of bouncing just meant that it was really, really, really tough to get a really good reading for the acceleration at any point in time, just the instantaneous acceleration. So instead of doing that, we decided to move on to a velocity-based approach because the velocity, I mean, you would expect that that would sort of integrate in the air and we would get all sorts of values. But because it was being sampled at such tiny time slices, we just found that very large outliers really didn't lead to enormous changes in the velocity. So we found that it was just a more stable measurement. And this was the approach that we took ultimately. And another problem was just in general, we're just dealing with real-time systems. So before we were saying, you know, we have a servo that we can control, and it can change infinitely quickly. So it can go from some theta value to another theta value instantaneously. In reality, this is just not the case at all. In reality, the servo can go from the min theta to the max theta, and it takes approximately 250 or 300 milliseconds to get there. We changed the theta range to be really, really small. So like, because it turns out, you know, the brakes are only effective within a very small range. But even so, just beyond that, it was still very unresponsive, and it took a long time to change. So basically, what we did here is we changed our braking calculation to work more with this less responsive servo arm, so that it would only actually change the theta value periodically at approximately every 200 milliseconds. And we saw that this actually gave us a better result there. So I guess are we just going to show a short?
Yeah. So we're going to present it later out in the hallway, but we want to do just one quick video right now because it looked like someone just waxed the floor, so that could cause slipping issues. So go ahead and click it. So Brian's about to accelerate it. Let it go, and nothing topples, and it doesn't hit the wall. Surprising. So general accomplishments, we were able to integrate all of our components together into one big system, all components from scratch. We were able to model and simulate our system on a computer first and get an idea of what the algorithm should be. We were able to get an algorithm that can properly break the system and keep any object that's on top of it from toppling over. And yeah, I mean, that's... Afterthoughts. So one of the main things would definitely be better sensors, because there were a couple things, so like the accelerometer issues that we were having, the velocity sensors we were having, and also the fact that the distance sensor only samples at a 7 hertz rate. So sometimes that's a little slow if you're moving at a fast enough speed. Things to add on in the future that would be nice would maybe be a more intelligent object avoidance. So that would, of course, require something a little bit more intelligent, like a camera that can actually figure out what it is that is in front of it, and a steering system. So ours is just, it goes in a straight line and it tries to stop. But for object avoidance, it would probably need to steer. One thing that would have been nice to have would be self-propulsion, because there were some times where it would slow up even though there wasn't something in front of it, just because it needs to apply a certain maximum velocity, otherwise it won't stop within 5 meters. So if this happens while it's in the middle of the hallway, then it could just slow down before it even gets to the wall, and then nothing happens. But one thing that I think would have been really useful would be a user interface that we could have used to actually debug, mostly because in our case, for a lot of the other projects, they were able to use laptops to get all their values that they were using and log data. For us, we couldn't really put a laptop on our board and then throw it at a wall. Not very practical. So it was very difficult. We would sometimes have a laptop on it, but you'd have to push it very lightly. But having an actual user interface that we could look at would have been very helpful. So right now, is there any questions before we go outside to do the demo? The total, you mean between each loop iteration? The delay of... Oh, what was that? Do you remember?
Well, it took a long time for the servo to we don't actually have an exact value for how long it took the servo to begin responding, but we know that the delay between when it got, in order to actually affect any real change, it took approximately 150 to 200 milliseconds to really get any real value at all. To get to the maximum value, it was even a little bit longer than that. It was probably around 300.
And the change of theta algorithm in there, we were setting the loop to round every 50 microseconds. So the theta was reset. Well, in the earlier trials, the theta was reset every 50 millisecond, and the sensor will pull as fast as the processor can do. And but unfortunately, even if the theta was changing 50 microsecond, it take 150 millisecond to 250 millisecond for the servo to actually go to the theta. So we keep missing that theta at the early stage of the project. But I think our later approach was solved to that problem.
Yep.
So you choose the
Arduino.
Nano?
Yes.
And what is the reason to do that? And you mentioned like you don't have an interface. Just because of you choose it and you don't have an interface? Or?
Yeah, we chose the Arduino Nano just because it would be smaller. Really, any of them would have worked. It was more so that it just fit better inside the whole system without sliding too much. Yeah, small form factor. Did you want to say something?
Yeah, I'll just say something. I mean, one of the things we could have integrated would be just some shield that would log it to an SD card or something like that, but we didn't actually have time to really get that on board. And we did actually do some sort of a crude user interface that would allow you to sort of select between different cylinder properties, but in the end we sort of had to reroute our resources and change things. No, it's right in there, yeah.
It's right here, right on this breadboard here.
Yeah. Another problem you could see with that actually is that the accelerometer is mounted right on that breadboard right there. There are no shock absorbers, so I mean it's going to be taking all the bumps. So that's another problem with.
Sorry, can I ask because like in the lab you guys using the SB reel, right? So this one's so big that you can fit a whole SB reel on with wireless, whatever you can confirm on using. So that's why I'm saying, like,
right.
The power trade-off or something that you choose Arduino over like the bigger platform.
Well, in the labs, we had a lot of problems with SBRIO of networking and whatnot. It would take, some cases an hour just to get it to connect to a computer. So we figured this would be a lot easier to interface with rather than dealing with one of those.
The object itself has a sensor?
No, there is no. This is just it by itself.
So the dynamic part is purely modeled?
Yes.
Yeah.
Yes.
We were attempting to put the accelerometer kind of on top of the cylinder at the beginning, and once it sends a tilt, it will send an interrupt to the board. But in the end, Will was so busy on trying to get the delay in the theta to work with our system, so we have the interrupt enact on the board, but except the sensor wasn't put on the on top of the cylinder.
Any more last questions? All right, then we'll go outside and do demo.
What is the limit velocity you can do that?
It limits the velocity through the acceleration.
It's an impossible case, like when the distance is not, because we can only sense 5 meters. So if you push it a little too hard.
Come on.
That little velocity before we even started, really.
Yeah, I think it was just going too fast at that point.
We even have a false proof. So if you're accelerating it too fast at the beginning, it was trying to slow you down, because we'll enter those impossible cases that the given distance that the sensor can sense, it would be impossible for us to slow down enough to have the cylinder not top over.
No.
Nobody saw that.
Yeah. There was nothing that happened.
It's the one that edited the video.
Sir?
Hey, is the floor different today? The floor was waxed.
Oh,
Yeah, so yesterday when we were testing it, the floor wasn't as clean.
There are lots of variables.
Yeah. See, even by just wiping the wheels, we could get those results.
Yeah, it was.
Oh yeah.
What is the beam width of this distance sensor? Did you measure that?
Oh, it's pretty narrow. So it'll.
So it's not. We're
It
not
could
affected.
maybe see me right now, but right now it wouldn't.
Yeah.
So like
Might,
in front.
might be seeing Praneet.
Yeah.
Well, Praneet's not that far from the wall, so here, just back off Praneet.
It'll.
It's going a little bit to the.
Yeah, the distance sensor is actually I use them to sense snow depth
Probably it would stop.
in the railroad. So we didn't ask for a very high sampling rate. It was sampling at 6 hertz. But for our application, we actually wanted to sample faster.
Yeah, it should never not break this hard part.
It's breaking really. I mean, it's very dependent to the floor as well, because sometimes the floor gets a little slippery. It actually slides.
And there's different noise every single run.
Yeah.
So.
Oh, the wheels slip when it's
Yeah, and so it basically locks the brake when it's not supposed to. So that's the difficulty we have with the friction. So we count for friction on the floor, but not really between the wheel and the floor.
What are you doing now? We have 5 minutes.
Is there like one parameter that we can choose to have it? It seems like the last, well, before we left, actually we changed one parameter.
Yeah, it just has more grip on the floor today because
Yeah.
it's clean, so it's not sliding.
Can we get some dirt from outside?
Yeah.
Dirty other piece of
Yeah.
No, I don't know the frequency of the sensor.
Yeah, I can see the distance sensor.
It's ultrasonic, that's all I remember.
Probably
7.
No,
that's just
the sound. The sound.
Okay, yeah.
You're doing a spectral analysis. That's a real.
Hold back for 1 second.
I didn't realize you guys were
1 second. That's fine. Or, you know what? Go ahead and
I'll
go.
watch.
If you want to watch, sure.
We're gonna need some.
Yeah, wait, right. Everyone hold back. Don't come. Oh, maybe.
for some reason.
Well, I think it's because he walked in front of it, so it,
Yeah, let's say that.
Do you want to start from closer?
Perfect cover up.
The parameter down, you guys said. Probably a little too far for today's. I think
That's what you need, like something like this, or you know, like actually.
so. When we got
Now the floor's dirty.
The video was taken last night when we're doing consecutive runs that was actually doing pretty well. So this happened in the past, like the second day, it was sort of a little different from last day due to
I suspect noise in the distance sensor.
could be, yeah.
Alright, I think I'm gonna grab the water now.
if it's going from there to there, it may be 1.5 seconds.
No, but what I mean.
I don't think it's that bad. Accelerometer, there's a...
Yeah.
I think that's a good ending.